In this lesson, we'll finish learning target number 6, describing acids and bases, focusing on the Bronstead-Lowry theory. The Arrhenius theory of acids and bases that we've been using has several limitations or inaccuracies. The first being that it defines acids as ionizing or falling apart to produce H pluses when dissolved in water. The problem is that free H pluses can't be found by chemists in solution. If you think about what an H plus is, it makes sense. You take a hydrogen atom, which is one proton and one electron, and you remove the electron. So you just have a proton. It's very tiny, and it's got a full plus charge on it. This means that it immediately gets attracted to and form covalent bonds with water. It forms a covalent bond because the hydrogen wants 2 electrons to be stable. It actually gets attracted to the lone pair of an oxygen. This creates an H3O1+, known as a hydronium ion. Now chemists find many hydronium ions in acid solutions. Arrhenius theory treats water just as a spectator. We could represent it by using this first equation here, where we have hydrochloric acid ionizing into H pluses and Cl1 minuses, but there's water in the beaker. Because we have water on the left and water on the right, it cancels out in the overall ionization equation. But because the H plus forms a chemical bond with the water, we have atoms that are being rearranged, and we make an H3O+. So this is the most accurate way to represent the interaction with hydrochloric acid and water. The second limitation with Arrhenius theory is that it does not explain the behavior of several compounds such as NH3 being a base. Using Arrhenius theory, ammonia should contain OH1 minuses, but it doesn't. We know ammonia is a weak base because it turns phenolphthalein pink and litmus blue. Ammonia doesn't ionize in water. It actually does a chemical reaction with water and makes hydroxide ions. Here's the balanced chemical equation showing that. The third thing is that Arrhenius theory only explains acids and bases in aqueous solutions, but there are several acids and bases that exist as gases. Here's an example of an acid-base reaction in the gas phase. We take ammonia gas and hydrochloric acid as a gas. They will actually neutralize each other together and make ammonium chloride solid. Don't get me wrong, the Arrhenius theory is a pretty good theory. It explains a lot of the interactions between acids and bases. You can use Arrhenius theory when you clearly have an Arrhenius base. That means it contains OH1 minuses, and you can clearly do a double displacement reaction. When you can't do a double displacement reaction, or you don't have a clear Arrhenius base, use the Bronstead-Lowry theory. It was created to address the problems with the Arrhenius. They define an acid as a substance that can donate a proton, and a proton in this case is an H1+ ion. It's not a proton being removed from the nucleus of an atom, changing what kind of element that you have. They define a base as a substance that can accept a proton, and the bases usually do this by attracting the H1+ with an atom that has a lone pair of electrons. Using these definitions, let's write a balanced chemical equation showing H2S acid reacting with water in example 1. In this reaction, there's no clear Arrhenius base. no chemical that has OH1- in it. So I have to use Bronstead-Lowry theory. It tells me in the question that the H2S is an acid. That means it's going to lose an H+, and becomes an HS1-. Now the charge changes. Don't forget to do this. You're losing not just an H, but an H+. Because H2S has a 0 charge on it, there's no charge indicated, and it loses a 1 positive, it will move down on the integer scale to a 1- charge. Because the water is the only other chemical in the reaction, and H2S was identified as the acid, water in this reaction is classified as a base. Now this might seem a little weird, but remember that the oxygen has 2 lone pairs on it, which allows it to attract protons. When the water accepts the H+ from the H2S, it's going to become a hydronium ion, an H3O 1+. Remember, you're not just adding an H, you have to increase the charge by 1 in the positive direction. Bronston and Lowry recognized that most chemical reactions can go backwards under the right conditions. They described the products of acid-base reactions as conjugates. It describes what the chemicals would do if the arrow was flipped and the reverse reaction occurred. The conjugate base is defined as the acid after the proton is removed. So in example 1, that would be the HS1-. We'll designate it the conjugate base by using the short form Cb. Now the conjugate acid is the base after the proton has been accepted. Remember, water was the base, so the H3O1+ is the conjugate acid, or designated Ca. If the reverse reaction happened, let's describe what would occur. The H3O1+ would actually be donating an H+ to the CS1-. The H3O1+ would convert into the water after the donation. Because the H3O1+ is donating a proton, it would be the acid, but in the reverse direction, hence conjugate acid. Because the HS1- would be accepting, it's known as the conjugate base. Bronston and Lowry also defined what a conjugate acid-base pair are. They describe 2 molecules that differ only by a proton, or an H+. There's always 2 conjugate pairs in an acid-base reaction. Here we have an H2S and an HS1-. The only difference between those 2 chemicals is an H+. Here we have the acid and conjugate base pair. The water and the H3O+ make up the second pair. We have the base and the conjugate acid. Finally, Bronston and Lowry described acid-base reactions as a proton transfer between 2 molecules. And we see that in example 1, where an H+ is taken off the H2S and given to the water. In contrast, remember that Arrhenius theory described acids and base reactions as acid plus base produces salt and water. Let's try out example 2 together. Here we're asked to show water reacting as an acid with water reacting as a base. Now, in example 1, you saw water reacting as a base. But water can also act as an acid using Bronstead-Lowry theory because it has H+'s it can donate. When this water loses an H+, it will become an HO1-. Well, that sounds very familiar. Just rearranged in order, we write down OH1- or hydroxide. Because it's the acid after it's done its donation, the hydroxide is known as the conjugate base. Now this makes sense because hydroxide's usually a base. When this water accepts the proton, then it will become a hydronium, or an H3O+. Because it's the base after it's accepted the proton, it's known as the conjugate acid. My first conjugate acid-base pair is between the acid and the conjugate base, and my second one is between the base and the conjugate acid. For your assignment, complete the acid-base reaction worksheet that you printed out with this note.